Hello everyone, and welcome to the Lab Extension Post Lab. This is actually a big one in this unit. We're going to lay a lot of groundwork on the ideas that we're going to employ this entire unit, so this is an important one to watch carefully. Now, in the lab extension, we created a graph of velocity versus time for the cart moving down the incline. And we found that it was a very nice graph, a very linear graph. And not only was it linear, but it went through 0, 0. And as we've learned in the past, when you have two variables that you graph and they create a linear graph that goes through 0, 0, it means they are proportional to one another. So we would say here that for the cart rolling down the incline, the velocity is proportional to the time. So it's definitely a very set relationship. If you allow it to roll for twice as long, it will be going twice as fast. 3 times as long, 3 times as fast. Right? Not as complex as the position relationship, but a nice straight direct proportion. Now, of course, we can create a y equals mx plus b math model out of our specific graph here. The y variable is what we graphed on the vertical axis, which is the velocity, and that equals the slope of your graph. Now, I'm going to use the theoretical slope. You should, of course, write in your slope. The theoretical slope here, for reasons which you'll find out in the next unit, it should be about 170. Units for that slope are rise over run. So the units of rise are centimeters per second. The units of run are seconds. Now, here comes perhaps the biggest question in this entire unit thus far. What does that mean? What does it mean that the slope of your graph of velocity versus time is 170 centimeters per second per second? Well, let's think about what this slope is. This is a graph of velocity versus time. And to find a slope, you need to choose 2 points. And of course, you generically find a slope by doing rise over run. So, in this graph of velocity versus time, the rise tells you how much your velocity changes. Right? The change in velocity, remember that delta symbol? And the run tells you how much your time changes. So the slope of this graph is telling you how much your velocity changes with a change in your time. So let's go back to the number, 170 centimeters per second, velocity units, per second, time units. So what does this mean? Well, this is telling you that every second the cart's velocity increased 170 centimeters per second. Now think about that for a second. It's not telling you how fast the car's going. What it's telling you is how fast the car is getting faster. Let me say that again. It's telling you how fast the car is getting faster. Your car is getting 170 centimeters per second faster every second that goes by. Wow, that's pretty deep, right? Because here we have a ratio and another ratio built into it. I mean, that's a pretty deep idea. This is an idea we're going to have to work on for quite a bit to really get the meaning out of. It's another one of those things that we give a kind of a common name, but we really don't understand what it means a lot of times. And so we're going to really work on what this is. Again, it's telling you how quickly your velocity is changing. Well, what do we call that? In common language, we call that the acceleration. And it'll be denoted in an equation by a lowercase a. And it is a vector, so it has an arrow over the top. Although the vector nature of acceleration is going to be difficult for us to figure out. We're going to do a whole activity on that in a day or two. So, we're going to define the acceleration to be the slope of a graph of velocity versus time. And since slope is rise over run, we can write that out in symbols as acceleration is the change in the velocity over the change in the time. Or in math language, it's the rate of change of velocity. Whew, that's a deep one. Remember that velocity is itself a rate of change. Velocity is how quickly your position's changing. It's the rate of change of position, how many miles you go every hour. So acceleration is how quickly your velocity is changing. Every second, the cart got faster 170 centimeters per second. So this is a very deep idea that we're going to talk a lot about in this unit and do a lot of things with, a lot of MOPs, a lot of activities and things, but we'll get to it as we go here, but it's a pretty deep meaning. Let's finish off the y equals mx plus b math model here. First thing is we can actually reduce these units. Actually makes it harder to interpret, which is why I left them this way while we were trying to decide what the slope meant. But remember here that line, right, means divide. So this is a centimeter per second divided by a second. And if you remember your fractions, dividing by something is the same as multiplying by its reciprocal. So a centimeter per second divided by a second could also be written as a centimeter per second times 1 over seconds. And now you can see what the units will be. Centimeters times 1 is a centimeter. Seconds times seconds is a centimeter per second squared. So we're going to reduce these units down. Logger Pro wasn't smart enough to do that, but we are. We're going to reduce them down to centimeters per second squared. But it's sometimes helpful to remember where these units come from, because it's really hard, again, to interpret what this means without those units, without the idea of a slope, a rate of change of the velocity time graph. So here we are now with our new reduced units. So this is y equals m. So the x variable is what we graphed on the horizontal axis, which is simply time. The y-intercept of this graph was 0, which kind of makes sense, because when the time is 0, the velocity is 0, because we started the cart right next to the photo gate, right? So it started from rest. So this then becomes our specific math model. And we have a meaning for the slope, a very deep meaning, and a meaning for the y-intercept. We can also make a general math model, which is going to come in very handy in this unit. We now know that the slope of the velocity time graph is the acceleration. But one other little idea here. We started the cart right next to the photo gate. What would happen if we started the cart several centimeters behind the photo gate? Okay? In that case, that would mean that when it got to the photo gate, it was already moving. So what would change about the graph? Now, in class, I'm going to show this to you, but you're going to have to think about it as a thought experiment here, right? Because I can't do this. So, is the acceleration going to change? Well, no. The cart's going to speed up just as fast as it sped up before. That's got more to do with the angle of the ramp. Right? What'll change is that it'll already be moving when it gets to recording. So at 0 time, it won't have 0 velocity. It'll have a y-intercept now. Same slope, but now it'll have the y-intercept. So what does this y-intercept tell you about the motion of the cart? It tells you how fast it's going initially. We're going to call that v sub o. Okay, v with a subscript of o. You might remember we did that with position, right? Initial position was xo. So initial velocity is vo. This is the y-intercept of a graph of velocity versus time. It's also the initial velocity. It's the velocity it starts out with. So, with that idea and knowing what the slope now is, we can create a general math model. So we're going to use y equals mx plus b because we've still got a straight line graph. The y is what we graphed on the vertical axis, which is the velocity. And actually, this is what we would call the final velocity. V sub o is the initial velocity. It's what we start with. V is what we end with. Notice this is the same way we did x and x sub o, right, before. That's going to equal the slope, but we just decided that the slope of a velocity time graph tells you how quickly the velocity changes, otherwise known as the acceleration. The x variable is the time, and we just decided that the y-intercept is the initial velocity. Now, if you were to look this equation up in a book, it wouldn't quite be written this way. Traditionally, these are switched around, and that's okay to do because this is addition, and addition is, of course, commutative. So we could write this equation as final velocity equals initial velocity plus the acceleration times the time. So here is a math model which relates the final velocity to the initial velocity, the acceleration, and the time. We're going to find more equations as we go throughout this unit, but this is our first one. And this is still a special kind of motion. Now, it's not constant velocity, okay, like the toy car lab was, but there is something constant about this graph, right? Its slope is constant. And we just defined the slope of a velocity time graph to be the acceleration. So this is an equation of one-dimensional, uniformly accelerated motion. Uniform is something physicists use to mean constant. Why don't they say constant? I don't know. But it's a pretty traditional thing to say that this is uniformly accelerated motion. And this is one-dimensional. Remember that one dimension is up and down the incline because we rotated our axes. So we've now had a unit with the toy car lab where we looked at constant velocity motion. Now we're going to have a unit where all of our motion is going to be uniformly accelerated motion, as exemplified by a cart rolling down an incline. Now, back when we did the original lab, the cart rolling down the incline lab, I told you that we couldn't yet explain what the slope of that position times squared graph meant. Now we have enough knowledge to know. Okay, let's compare the velocity time graph to the position times squared graph. So in our velocity versus time graph, the slope of that graph was 170, theoretically, centimeters per second squared. And we decided that that was the acceleration of the motion, right? The acceleration of the cart. It went 170 centimeters per second faster every second. Well, let's look at the slope of our position versus time squared graph from the original lab. Theoretically, that was 85 centimeters per second squared. Well, is that the acceleration? No, that's the acceleration, 170 centimeters per second squared. Now, it's got the same units, but look at the number. Right? The number is exactly half of the acceleration, 1/2 of a. Look at your numbers. They're going to work exactly the same way. Look at your original slope from the position times squared graph. It'll be exactly half of the slope of the velocity time graph, the acceleration. So, I'd like you to go back into your notes, and in the post-lab notes, in that blank we wrote that said slope equals, well, now you can write in half the acceleration. And when you write the lab extension post-lab, when you're explaining what the, when you write the original lab report, okay, which is due soon, and you write what the slope means, all you have to write is, as we showed in class, the slope is 1/2 the acceleration. Boom, you're done. That's the meaning of the slope. Don't try to interpret the number. Just say, hey, the slope is 1/2 the acceleration. So I hope you enjoyed this very important lab extension post-lab, and you might want to rewind this one and look at it again, especially when you go to write the post-lab lab report.